Hello students, on last turn we saw the function of the PN junction and I told you that PN junctions are classified into the two types. One is the forward bias PN junction and second one is the reversed bias PN junction. Now we will discuss these forward and the reverse bias junctions in detail today. First we will take the forward bias PN junction. What is the forward bias PN junction? When a battery of EMF greater than the barrier potential is connected to PN junction in such a way that the positive terminal of the battery is connected to the P region and the negative terminal to the N region, then the PN junction diode is said to be forward biased. What is? That is, we know that there is always a potential barrier in a PN junction. What we have done, we have just connected one or an external battery which is having the potential greater than this potential barrier. How we have connected this battery? We have connected this battery in such a way that the positive terminal is connected to the P semiconductor or P side of the PN junction and the negative terminal to the N side of the PN junction, as you can see in the figure. Now, a potential difference V develops across the diode. This potential difference reduces the barrier potential and hence the junction resistance becomes very low. The holes in the P region and electrons in the N region now are repelled towards the junction. What actually happens here? The positive holes are now going towards the junction. Similarly, the electrons are going towards the junction, means they are repelled from the each terminal of the battery. Thus, the charge carriers in both the region acquire sufficient energy to cross over the barrier potential across the junction. Thus, the flow of electrons to the left side and flow of holes to the right side of the junction begins. The movement of the holes and electrons constitute two types of the currents. One is known as the hole current, which is represented by IH, and the current carried by the electrons is designated by IE and is known as electron current. In the region of P junction, electrons and holes recombine. For every electron hole recombination near the junction, a covalent bond of P type semiconductor connected to the positive terminal of the battery breaks. Now there is a breaking of the covalent bonds near the P junction. The electrons liberated enters the positive terminal of the battery and holes move to the right side of the junction. Similarly, more electrons reach from the negative terminals of the battery and enters the N region to compensate the electron lost by the combination with the holes at the junction. As we have seen earlier that there was a combination of the electrons and holes. So what was happening? In absence of an external battery, these electrons and holes were recombining, thus reducing the electronic charge. Now, what we have done? We have just enhances or increases the number of electrons by repelling them by an external source of EMF whose EMF is larger than the potential barrier. When this EMF is larger, definitely the electrons will overcome this energy barrier and more electrons will move towards the junction. Now, the electrons lost by the combination with the holes at the junction, these electrons diffuse through their junction and enter the p region. Here they again combine with the holes, thus a large current flows through the junction. Now we see the energy band diagram for forward biased PN junction. The energy diagram is shown in figure 3. Again, you know that in the forward bias, the barriers for the flow of electrons from N side is reduced and hence IR will increase with a value of Vx. X here represents here external. The net current in the forward bias will increase with voltage, and the energy band diagram of forward bias you can see in the figure. In this figure again, EVP represents the valence band of P semiconductor. EF is here same as Fermi level. EC is the conduction band for the P junction, and on right hand side EV is the valence band for N type of semiconductor. EC is the energy of the conduction band in N type of semiconductor, and the voltage is reduced by an amount of delta E minus EVx. Now next is the reverse bias PN junctions. A PN junction is said to be reverse bias when the positive terminal of the battery is connected to the N region and the negative terminal of the battery is connected to the P region of the PN junction diode. What we have done here? We have just here reversed the terminals. Here positive terminal is connected with the N region and negative terminal is connected with the P region as shown in the figure. So when a battery is connected in reverse mode to the PN junction diode, a potential difference of V volt is applied across the diode. Thus, potential difference is added in the barrier potential, which in turn increases the potential barrier, that is the energy of the potential barrier increases here. Hence, the junction resistance increases. In forward bias, the junction resistance was decreased, whereas in the reversed bias, the junction resistance rather you can say increases. The holes and electrons in the P region and N region respectively are attracted by the negative and positive terminals of the battery respectively. In forward bias they were repelled, and in reverse bias they are attracted by the terminals of the battery. Thus, both holes and electrons are displaced away from the junction. As a result of this, holes in the P region and electrons in the N region cannot cross through the junction. Means now they are going away from the junction. Since they are going away from the junction in respective direction, so they cannot cross the junction. Therefore, the flow of current in a diode is almost stopped. If the reverse bias is increased to a high value, the covalent bond near the junction break down and a large number of electron hole pairs are liberated. Thus, the reverse current increases abruptly to a very high value. This phenomena is called breakdown. Please note it. This phenomena is known as the breakdown. So what is the breakdown? Breakdown is a abrupt increase in the potential barrier, so that the flow of charge or flow of current stops in the reverse biased PN junction. And the value of reverse voltage which we have applied here is called avalanche voltage. What is this called? This is called avalanche voltage. Or you can also call this at the Zener voltage. Z-E-N-A-R. Zener voltage. In the reverse bias, the thickness of the depletion layer and the junction resistance increases. Energy band diagram of reverse biased PN junction is shown in the below figure. During the reverse biasing of the PN junction diode, the energy barriers increases by an amount of EVX. X here is external voltage. In the forward PN bias junction, the voltage was, or the energy barrier was decreased by an amount of EVX, whereas it is increased here the reverse bias PN junction. And hence a very small constant current IR can flow and IG is not affected. Remember, here generation current is not affected. The net current, that is IG minus IR, will be very small and constant. Again, here from the figure you can see that here EF is the Fermi level, EVP is the energy of valence band in P semiconductor, ECP is the energy of conduction band in the P type of semiconductor, EVN the same thing for the N type of semiconductor, and ECN is the same type of the energy for N type of semiconductor, and the energy is increased by an amount of E multiplied by Vx, so total energy becomes delta E plus EVx. This completes your reversed and the forward type of biased semiconductors. On next turn, we will take the superconductors. Thank you.